Today we continue discussing problems relating to thermal conductivity of metals. The first problem that we are going to do today is rather elementary, which based on the definition of thermal conductivity via the Fourier equation, steady state equation. So, we are asked to calculate the heat flux through a sheet of brass sheet .5 millimeter thick, faces at 150 Celsius and 50 degrees Celsius. Thermal conductivity of brass is given to be 120 watts per meter degree Kelvin. Area of the sheet .5 meter square. So, we have the standard equation. We are asked to calculate heat energy, heat flux and heat energy per hour. Heat flux is defined with respect to unit area. So, it is given by Q dot is minus K dt by dx, where this is the temperature gradient. So, we are given that we have the thermal conductivity, which is 120, and then dt by dx across 7.5 we have a gradient of 100, 7.5 millimeter. So, into 10 to the power minus 3. That would work out to be 80 into 10 to the power 4 joule per second. And taking the area into consideration, the heat energy transmitted per hour is just this quantity into the area, which is 0.5. So, that would give you, that is per second into 60 per hour. So, that will be 2.88 into 10 to the power 9 joules per hour. The next question is on thermal conductivity of metals. We are asked to prove the thermal conductivity, the kinetic theory expression for thermal conductivity for a perfect gas as 1/3 C L V bar, where C is the specific heat, L is the mean free path, and V bar is the average mean velocity of the gas molecule. So, this is the expression that we will adopt for discussing thermal conductivity of a metal as well. So, we consider two sections at temperatures T and T plus delta T. So, there is a temperature gradient along this direction. So, let us call this x direction. So, there is a temperature gradient, and let us take these two sections, call them sections A and B. And the mean free path L is V x times tau, where tau is the relaxation time or collision time, and V x is the average x component of the speed. Therefore, if this section is separated by a mean free path, then delta t is dt by tx times V x bar tau. Now, we calculate the number of molecules which transport energy, thermal energy, to the two sections by moving, by carrying heat along the x direction. So, number of molecules that cross the section A crossing section A per second. This is, we know that is half n V x bar. And these, where n is the number of molecules in unit volume. Now, therefore, the heat energy and then per unit temperature gradient, K J by, since we have considered unit area already. So, this is just this, and therefore, it just comes as, and V bar tau is L. So, it is 1/3 C L V bar, which is what we are asked to prove.